Hey guys, Houston Math Prep here. I am joined by this function f of x. It's got its graph here. Let's say that I wanted to approximate the graph of this function f of x with some polynomial. Why would we do that? Well, polynomials are really easy to work with. First of all, they're easy to plug into. Everything's a whole number power of x. It'd be easy to plug stuff in, get a value out of it. The graphs are well behaved. They're smooth, they're curvy, there's no jumps, no holes, doesn't have any asymptotes going on. Also, because they're whole number powers of x for every term, that means they're super easy to differentiate and integrate. Everything would just be some sort of a power rule, whereas this original function might not be like that. And of course, the most important thing is that polynomials are a power series, right? A power series is just a bunch of whole number powers of x with coefficients, and that's a polynomial. So we're going to use a polynomial to approximate this graph f of x. And we are going to call our polynomial p of x. We're going to start building at the y-intercept. So I've got my y-intercept here. It's just at 2 on this f of x here. So I want my polynomial obviously to go through the same point, have the same y-intercept as my original f of x, my original function. So I need the function, my original, at x equals 0 to be the same as my polynomial at x equals 0. I want those things to be the same. So if I just want a single term polynomial that goes through that y-intercept, then I could say my polynomial, my p of x, is just equal to f of 0, whatever that y value is. So it's just going to go right through that point, and it'll be a horizontal line. My polynomial here is just a constant function. So in terms of polynomials, we're going to go ahead and call this p0 of x, because this is really degree 0. In power series term, this is the x to the 0 term, the constant term. So let's say we want our line to be a better approximation. So not only do I want the y values to be the same at that point, I also want the slopes to be the same, and that will be the derivative at that point. So you can imagine if I'm approximating with a line that has a particular slope, then I would need something that looks like y equals mx plus b, right, from algebra. So we'll need our polynomial to have a slope, f prime of 0, and we'll need its y-intercept to be f of 0. So in other words, our polynomial this time will be f prime of 0 times x plus f of 0. This is just a fancy way of writing y equals mx plus b with the correct values in place. Here's my slope, here's my y-intercept. We'll go ahead and get a different approximation, so we'll get a line with the same slope. It'll be tangent to that point there. And in terms of polynomials, you notice we have a constant term, but now we also have an x term. So we'll go ahead and call this polynomial now with this extra term p1 of x. So now let's take this a step further. Let's say we want the same y-intercept, we want the same slope, which we already have here, but there is some bendiness to the function here, right? Which we call concavity. So I want to match the bendiness at that point as well. I want to match the concavity, so I want the same concavity in my polynomial as I have in my function. So I will need not only the y-intercept and the slope at x equals 0 to be the same, but I'll also need the second derivative at 0 to be the same for my approximation. In order to get any information that is non-zero out of my polynomial for concavity, in other words, if I take the second derivative and get something that's not 0, the only way to do that is to have at least an x squared term in my polynomial. So what we'll need to do is just take a guess, and based on how the formula's gone so far, maybe we say that my polynomial is the second derivative at 0 times x squared plus the first derivative at 0 times x plus f of 0. Maybe the order of the derivative just matches the power of x in the term. So we'll take that as a guess and we'll go with it. So we're going to check to see if all these things are true with our guess. So first thing I'll need to check is f of 0 equal to p of 0? Well, if I just want to find p of 0, I'd plug in 0 everywhere for x here, so this first and second term would become 0. We'd get simply that p of 0 is f of 0, and that's what we wanted. So the first thing checks out okay. So then we'll need to check next, is the first derivative at 0 on the original function the same as my polynomial's first derivative at 0. So we'll need to check p prime of 0. I haven't figured out the derivative yet, so let's do that. Remember, each thing's going to be a power rule, so the derivative of this term, the 2 will come out in front and the power will go down by 1, so we'll get 2f double prime 0 of x, and then this just being an x term, we'll simply get f prime of 0 for the derivative of that. The last term, obviously, the derivative of a constant is 0, so we get this for our p prime, and now I wanted to check, remember, p prime of 0 and make sure that's the same as f prime of 0. So if I plug in 0 everywhere x is, there's really only one x term here, so that would just give us 0 for the first term plus f prime 0. And that one, it looks like it works out as well. So our second one checks. The last thing we need to simply check here, is our concavity the same? So if I want to find concavity, that means I'll need the second derivative. So going off of my first derivative that I have here, I go ahead and take the derivative. 2f double prime 0 times x, the x will drop off, that will become a constant there, and then f prime of 0, that's just a constant, so the derivative of that will be 0. So my p double prime of 0, plugging in 0 everywhere there's an x, there's not actually any x to be plugged into here, so really this just stays 2f double prime of 0. And what I wanted was my p double prime of 0 to be just f double prime of 0. So what ended up happening here is we've got twice as much as we want. Okay, so our guess is off by a factor of 2, at least just for the concavity. It turns out everything else was okay. So what we'll do to fix that is simply just change our x squared term in the original, which was what gave us the concavity off by a factor of 2. We'll just go ahead and divide that by 2, and we'll get that our second degree polynomial that approximates the function just has an x squared over 2 in that term, and then everything matches up okay. And if we go back and graph our polynomial on top of f of x, you can see that our concavity begins to reflect exactly what's going on with the function itself at that point. So what we would keep doing is we would just continue to set more and more derivatives equal to each other and take further and further guesses. We won't go through fully what we went through with our polynomial degree 2, but our polynomial degree 3, if I wanted more information about the change in concavity, then I would need an x cubed term. Now you can imagine what we're doing when we get down to this last step to see if all of our derivatives are equal at x equals 0. What will have happened is we will have taken the derivative 3 times. So the first time I take the derivative, in other words, a 3 is going to come out, right? And then the next time I take the derivative, a 2 is going to join the 3 that I already have out there. And then the third time that I take a derivative, there's going to be really a 1 that comes out, although that won't change things. And so we'll get 3 times 2 times 1 outside, and we'll be off by a factor of 6. And so then if we take our x cubed term and divide by 6, we should have all of these derivatives equal to one another. So what you may further notice is if I keep going up, let's say then I have some sort of x to the 4 term and I have to take 4 derivatives, then I'm going to get a 4 coming out and a 3 coming out and a 2 and then a 1 finally for the last derivative. These expressions certainly do look something like a factorial, don't they? So we can start to see what happens that we're off by a factorial for each of our terms. And so if we keep generating more and more terms using this pattern, then we get what's called a Maclaurin series. This polynomial, if we have an infinite number of terms, is called a Maclaurin series. And that's when we approximate a function around x equals 0, around its y-intercept. Obviously, we assume that the function and its derivatives are all defined at 0. So you can see kind of this pattern here. In each of these terms, you've got so for example, in this term I have a second derivative, I have a second power of x, and I have a 2 factorial. So you notice the power, the derivative, and the factorial all match in each term. Remember that 0 and 1 factorial are both considered to be 1, so that's why we actually don't have over 1 here. But this is the pattern for these. If we only use a specific number of terms and we don't use an infinite number of terms, then we call that a Maclaurin polynomial. So Maclaurin series means we're using an infinite number of terms. Maclaurin polynomial means we're stopping at some particular power term here. So you can see my second degree polynomial is telling me to stop at the x squared term, which is what I have written here. If we go back to our graph here, you can get a better idea of, so this was the graph we left off with our second degree approximation of this function. Here's our third degree approximation if we had included an x cubed term. Our fourth degree approximation would look closer still. Fifth degree approximation starts to get very, very close. You notice especially around the point that we were trying to approximate around, which was the y-intercept. So let's just do a few common examples of Maclaurin series that are good to have seen. So we're going to find a Maclaurin series here for f of x equals sine x. So our function in this case is going to be sine x. And remember, for our formula that we just showed, we're going to need some derivatives, however many we need to establish a pattern. So I'm just going to do several of these derivatives. So I'll go ahead and say f prime of x, we'll do that. What is that? That's cosine of x, right, for that one. The second derivative of sine x, so the derivative of cosine x would be negative sine x for this one. We'll keep going. So the third derivative then, which would be the derivative of what we just found, the derivative of negative sine x would be negative cosine x. The fourth derivative, remember, once you hit the fourth derivative, we use the little parenthetical notation for the order of the derivative we're taking. So that's the fourth derivative. And fourth derivative gets us back to sine x. So we're going to just repeat every four derivatives. So the fifth derivative is going to be the same as the first derivative that we found 4 ago. So that's going to be back at cosine x again, right? And if we're finding a Maclaurin series, remember, we're going to be using 0. We're approximating around 0. So I'm going to use my coefficients are going to deal with f of 0 and f prime of 0, etc. So f of 0 is going to be sine of 0, which is 0. And my first derivative, so f prime of 0, would be cosine of 0. Cosine of 0 is 1. Then the second derivative, the nice thing about Maclaurin series is that we're just plugging in 0, and for most things, plugging in 0 is easy to do. So we'll have negative sine of 0, so that's still 0. For this one, the third derivative at 0 is going to be negative cosine of 0. And we know cosine of 0 is 1, so this will be negative 1 for this one. We will get a fourth derivative at 0. You might start to see a pattern here, right? So this is going to be back at sine of 0, and that's going to be 0. And then the fifth derivative, if we plug in 0, that's going to be the same as the first derivative when we plugged in 0, cosine of 0. And that's going to give us 1. So you can imagine if we kept going, right? The sixth derivative at 0 is going to be 0, and then I think you can tell that the next derivative is going to give us negative 1, right? So the seventh derivative at 0 would give us negative 1, etc. So what we'll do is we'll use these coefficients 0, 1, 0, negative 1, 0, 1, 0, negative 1, that pattern, to assign our coefficients for our Maclaurin series. So if we sort of move these over and move them out of the way, now we're going to be missing some terms because we have some 0 coefficients, right? So if we go ahead and say our Maclaurin series, I'll write it as p of x. So our constant term has a coefficient of 0, right? The constant term is going to be 0, so nothing there. My first derivative is going to give me my coefficient for my x term, so that will be 1x. Nothing for the x squared term. For the cube term, I have a negative 1 for the coefficient. Now remember, this is where we really need to start after the x term doing, so I'll say 1x cubed, negative 1 there, and then we need the factorial as well, right? So I'm going to clean up these 1s and negative 1s, but I'm just going to plug them in so you can see for the first time. So the x to the 4 term would be 0. The x to the 5 term would be back to positive 1, so we'd have plus 1x to the 5, and that would have a 5 factorial on the bottom as well. The x to the 6 term would be 0. The x to the 7 term, we'd have a negative 1 for that derivative value there. So we'd get negative 1 x to the 7 over 7 factorial. And if you can begin to see a pattern here, let's go ahead and clean this up. So we'll say our Maclaurin series for sine of x is just going to be x minus x cubed over 3 factorial plus x to the 5 over 5 factorial minus x to the 7 over 7 factorial, and we could keep going. I think you can probably see a pattern by now though, right? So you'll notice first we have all odd powers, so all of our even powers are 0. Obviously the factorial on the bottom matches the power. We also have an alternating series. So some interesting things here. We have an alternating series. We have all of the odd powers. If you've talked about symmetry of functions in the past, you might have talked about that sine of x is an odd function. You can see it in its Maclaurin series as well. Okay, so this is a super common function that we'll use, super common Maclaurin series that you'll see a lot. So that's a good one to know. So if we want to find a Maclaurin series for cosine of x, that procedure is going to be very similar to the one we just did for sine x. All of our derivatives will sort of cycle in the same pattern. This time we'll start with cosine x, then we'll cycle through the negative sine and cosine x back to the positive sine cosine x with that pattern, etc. So if we go ahead and plug in, so if I plug in 0 into the original function, cosine of 0 is 1. If I plug into the first derivative, negative sine of 0, that's going to be 0. If we plug in negative cosine of x and we take cosine of 0, now we get negative 1. And so any of these sine terms, so this third derivative and this one is going to be 0. Here, the fourth derivative using the other notation. So that one's going to be back to a positive 1. This one here for the fifth derivative, right, is going to then give us 0 again. So we'll just go ahead and say, so the sixth derivative at 0 is going to be then back to, if you can tell, negative 1, and then the seventh derivative, you can see we're back to 0 again, right? So we just kind of keep getting this pattern. So this time, my first term, you'll notice my constant term is not 0 like it was in sine. My first term here is just 1, so my constant is actually 1 for this one. My linear term, my x term, is going to be 0. Second derivative would be my square term, so that's going to be minus 1x squared. And then I need my 2 factorial on the bottom from the formula. My cube term will be 0. My x to the 4 term will have a positive 1, so I'll have plus 1x to the 4 over 4 factorial. My fifth degree term is going to be 0. My sixth degree term will be back to negative 1. There you can see kind of the pattern, I think, there. So I get this alternating series again, right? And I guess I can kind of clean this up if I just go back and get rid of my 1s there. You can kind of see. So this would be my Maclaurin series for cosine of x. You'll notice we're missing all of the odd terms now. This is the x to the 0 term, the constant term. Cosine, if you did symmetry of functions, maybe in algebra or trigonometry or pre-calculus, you were told this was an even function. Let's do one more example. You know, this one's a little bit different, but I think you will find it to be perhaps the easiest one of all. So we're going to find a Maclaurin series for e to the x, right? Exponential growth function. So if my function is e to the x, then the derivative is, that's right, it's e to the x, and the second derivative is going to be e to the x again, right? So we just keep getting e to the x for all the derivatives. So that's super easy. And if I plug in 0 for each one of these, what am I going to get? F of 0 is going to be e to the 0, right? Which is 1. And each of these, we're going to keep getting 1 forever, right? So the Maclaurin series for e to the x is basically the series where all of those values for all of the derivatives with 0 plugged in just give us 1. So my Maclaurin series for this one, I have everything as 1, right? So I have a 1 plus 1x, we'll just call it x, plus 1x squared, I'll just call it x squared, over 2 factorial, plus 1x cubed over 3 factorial, right? So all those derivatives in the formula just become a 1 when we plug them in because we get the same derivative for every single term. Okay, so we'll go ahead and finish up with my ellipsis there. So that's the Maclaurin series for e to the x. So here I've just written down for you in one place our common Maclaurin series that you'll see sine x, cosine x, and e to the x are all functions that you may want to know a Maclaurin series for a calculus or a differential equations type course. Remember, the big idea with these Maclaurin series is that you can use them to approximate a function, and as you take more and more terms, then you get a better approximation. If we use an infinite number of terms, we get an exact copy of the function. So here you can see my first degree approximation for sine, then third degree, then fifth degree polynomial, then x to the 7, x to the 9, x to the 11. We keep adding more and more terms, and then extending out from the y-intercept, we get a better approximation. And if we were to keep going forever, we would indeed get an exact copy of the entire function. Thanks for watching, everybody. Hopefully this gives you a good idea about Maclaurin series. We'll see you in the next video.